Hello, this is Junhao. Today I'm going to introduce our project. As you can see, the title for it is Feature Encoding by Location Enhanced Word2Vec Embedding for Human Activity Recognition in Smart Home. Here is our today's agenda. Firstly, I will introduce the IoT-based smart home environment. People are expected to live longer than before. WHO reported that the elderly population among the world is about to reach 2 billion by 2050. Therefore, some researchers are focusing on how to assist the old people to live better. The elders' health needs to be monitored and their daily lives also need some assistance. The IoT-based smart home is one approach. IoT, which is Internet of Things, based smart home technology has achieved rapid development in the past decade. Devices deployed in smart home environments can communicate with each other and somehow automate features in such environment. At the same time, due to the development of IT technology, more and more applications can be realized in smart homes rather than just switch on and off some devices. A relatively new concept of smart home was proposed, which put forward that occupants should live autonomously and comfortably with the assistance of digital devices that are installed in a smart home environment. The basis of such features is human activity recognition. For example, if the system recognizes that you are sleeping, it will turn off the lights automatically. Now we will discuss the HAR algorithms and current literature. HAR is human activity recognition. There is a lot of research using vision-based features for HAR. They use cameras to capture data. However, the classification scenario is for assisting occupants. Therefore, using cameras will have privacy issues which could make occupants feel uncomfortable, so that we do not recommend using this approach. There is another, more popular approach which is sensor-based approach. It uses sensors to capture human activity data. One subcategory of this approach is using wearable sensors such as smartwatches or smartbands. Limitations could be, firstly, if one occupant is asked to wear such devices for a long time, their daily activities could be interfered with. In addition, if they take off devices unintentionally, data could be lost, so that it is impossible to do classification. Another approach is to use ambient PIR motion sensors. The advantages of this approach are low cost, power saving, and the most important thing is that such sensors can be attached to the home object seamlessly. It is also very easy to implement, especially for the elders. Therefore, in this study, we adopt the data that was collected by the CASAS project. They used this sensor type to collect the occupants' daily activity data. Here is the segment of the data we used. We will talk about it in detail in the proposed method part. Feature encoding and selection is the basis to train a robust classifier. In the current literature, there are mainly two kinds of methods for processing features. The traditional method uses handcrafted features. They use data segmentation methods such as sliding windows to generate windows, then compute the duration of a window, extract the last sensor and the first sensor of a window, or the number of different sensor events in a window, and so on. The literature called this as handcrafted features because such features need expert domain knowledge to manually generate, select, and validate. This approach is not efficient and not robust to unknown data. Another approach is automatic features, which use deep learning methods to process the raw data directly. It is so-called end-to-end method because a neural network-based classifier can do both feature selection and classification. Such features are robust to unknown data. Although using handcrafted features achieved good results, they put a lot of effort on how to select and validate. In the literature, there are some studies using deep learning methods to use automatic features. Zhao processed the raw data directly to generate activity images. X-axis of the image is the size of the window, Y-axis is subject to the researcher. Y is the mapping between sensor and the coordinates. They achieved 0.951 F1 score for the 8 activities. Automatic features are fast and robust to unknown data. It is also end-to-end because the neural network can both select the feature and perform the classification. As an extension, Gojo posts an RGB activity image for feature generation. The color of the pixels refer to the time interval, and the color of the top two lines refer to the previous two activities that happened before the current activity. This method achieved 95.2% accuracy. There is a brand new approach for HAR in smart home environments, which is semantic. They use the frequency-based NLP encoding to encode features. For each sensor event, they extract sensor ID and sensor value, treat them as a word, and the sequence of events as the sentences. For example, M020 on is one word, representing one event. Many of these kinds of words will form a sentence. The feature vectors are lists of frequency of each word in each sliding window. This is also one kind of automatic feature. They use fully connected networks to do the end-to-end classification and achieve very good results. All right, let's summarize our motivation for this study. To somehow provide a more comfortable and automatic smart home living environment for Asian people, we need a robust classifier for real-life HAR. After reviewing the current literature, we selected to use ambient sensor data, and we would like to know how to avoid complex pre-processing steps and how to improve the current NLP approach for HAR. Because the semantic approach is a brand new area and it also adopts the automatic features. The current literature for NLP did not use word embedding models. They only used the frequency-based encoding, which was very basic encoding in the NLP area. Word2Vec is one of the popular word embedding models, which can generate feature vectors for each word based on the context. Compared to the frequency-based encoding, it can capture more domain knowledge and a context relationship in one sentence. In addition, some researchers were trying to incorporate users' location to improve model performance. However, the current method of NLP did not use the location information. Therefore, we would like to come up with an approach to add location information into event sequences to improve the performance. Now I am going to introduce the proposed method. We select to use the data collected by the CASAS project, which uses ambient sensors. Here is a segment of the data. Compared to the current literature of semantic approach, our selected data recorded the location of each sensor event, which provides the possibility for us to incorporate it. The data contains timestamp, sensor ID, location, sensor type, and sensor value. Here is the overall workflow. I will discuss each part separately in the following slides. First is word generation. For the non-location approach, we use the same approach as current study, combining sensor ID and sensor value as a word. For the location-enhanced approach, we further incorporate the location indicator of each sensor event into the word. For example, one word can be M001 bedroom on. After generating words, we index each word so that encoding them into numbers for the machine to process. Then we need to generate the event sequences. For the non-location method, we just simply put all the words into lists. For the location-enhanced approach, the location information is recorded every other event. Someone could ask, why don't we record the location information for every event? The reason is, if we use the location-enhanced word for every step, the vocabulary size will not be increased. This is the same principle as our human language system. Only the richer vocabulary can express richer semantics. After we generate the sentences for the raw data, we need to split sequences into sliding windows. Here, we select the sensor event window because we would like to avoid too many zeros in each window by controlling the size of the window. In the literature, 20 to 30 window sizes are always selected. We also experimented with larger sizes such as 50 and 75 to see the effect of larger sizes. For the Word2Vec approach, zero padding is used to pad those sequences whose length is less than the defined window size. As you can see, we compared the two encoding approaches. They generate different vectors. For the Word2Vec embedding, the vectors will be the embedding vector of each word. For the frequency-based vectors, each vector will be the frequency lists of each word in one sentence. We chose to use the text CNN architecture and modified it a little bit during the experiment. There is an embedding layer, convolutional layer, max pooling layer, and a fully connected layer. To evaluate our approach, we adopt the 80-20 split. 20% of the data will be our testing data. This is one of the best practices in the machine learning area. We totally have 16 activities. We deleted some of the activities in the raw data because they have few supported samples. The selected metrics are precision, recall, F1, and accuracy. We also look at the weighted metrics to avoid unbalanced label problems. Now let's discuss our main findings. Firstly, we compared the two different sequences encoding method under the non-location condition for different window sizes. We look at the precision, recall, F1, and the weighted version of each matrix as well. The origin bars represent the Word2Vec method performance. As you can see, for each metric of different window size, the Word2Vec is better than the frequency encoding for the window size 25 and 50. However, with the increasing window size, the magnitude of improvement decreases a little bit. For example, compared to window size 25, the increase of the weighted average F1 score of the model is 0.05 on the right-hand side, which is smaller than 0.1 on the left-hand side figure. Next, we compare the two different sequence encoding methods under the location-enhanced condition. As we can see, although the Word2Vec can still improve the overall performance because for most of the matrix, the orange bars are still better than the blue bars. The magnitude is very small. The reason is that the location-enhanced method has already improved the performance of frequency-based encoding. Now we compare the two different sequence generation methods under the frequency-based encoding method. It is obvious to conclude that the models with location-enhanced sequences achieve much better performance on each of the matrices for different window sizes. The same as before, larger window size, a little bit smaller improvement. Under the Word2Vec encoding condition, the improvement is also significant. The improvement is more obvious than the Word2Vec encoding under the location-enhanced condition. Therefore, it gives us the intuition that location-enhanced sequences can affect the baseline model more significantly than the Word2Vec embedding. That is, if we only choose one method from Word2Vec and the location-enhanced sequences will be better. We also compared the effect of different window sizes. In most situations, larger window size can have better performance. However, we find that under the location-enhanced condition, larger window size can even have a negative effect. Therefore, we cannot blindly increase the size of window size to achieve better performance. Our best model uses both Word2Vec and location-enhanced sequences generation method with SEW size 25. It achieves 0.77 weighted F1 score and 0.81 accuracy. To sum up, our experiment results illustrated that both location-enhanced sequences generation method and Word2Vec embedding can improve the classification performance and larger SEW size could be beneficial to the performance, but not always. In the literature, the big SEW size is not preferred because it is not good for real-time classification. The magnitude of improvement of location-enhanced sequences becomes small when using Word2Vec embedding, and vice versa. Our best model uses both location-enhanced sequence generation and Word2Vec embedding, with SEW size 25, which is considered as a small window size, so it is adopted. Conclusion and feature work. We used the NLP idea, which is one of the deep learning methods. So we can process the raw data directly to avoid spending lots of time on generating handcrafted features. Our study used Word2Vec to improve the current method, which used frequency-based encoding before. In addition, we incorporate the location information semantically when generating event sequences, and the results show that the location indicators can improve the model performance as well. Our best model achieves 0.77 weighted F1 score. It uses both location-enhanced sequences and Word2Vec with a small SEW size, which is good for real-time classification because of the short latency. However, the Word2Vec model has its own limitations. Firstly, it is static and context-free, so one word will only have one vector. But sometimes a word may have different meanings. For example, apple juice and the Apple Technology Company. The meaning of the apple is different in these two phrases. In addition, Word2Vec cannot handle unseen words. Another limitation is about our dataset. The dataset only records the activity data of one single occupant. Therefore, our classifier cannot handle multi-occupant activities. In the future, we will select the multi-user dataset to experiment with and try other dynamic word embedding models such as WordPiece and ELMO. We can also experiment with other classifiers such as LSTM to train the parameters of Word2Vec as well. Different data segmentation approaches can also be tested, such as time window, which splits data based on equal time duration. That's all. Thank you for listening.